Hello.
Um, um, Good
Hello, good
afternoon.
afternoon.
Good evening.
Good evening. So I'll start present. Am I audible?
Yes,
Okay. So I'll start presenting my screen. Please let me know if you can see it.
yes, now
It's
this
visible.
screen is visible.
Okay. We'll wait for a couple of minutes. If somebody else joins, then we'll start.
Mm,
Okay. 2 minutes more and we'll start, okay? Is it fine?
Okay,
Okay.
yes, ma'am.
Okay, so I'll start now. Uh, Welcome to this discussion session. Um, Firstly, I would like to know if all of you have joined, if you did go through the lectures for week 2 or not. Did you?
मल्टीपल वन नहीं देखा, बाकी वो दोनों वीडियोस देखे.
I'm sorry, can you please repeat?
I have not completed multiple linear regression,
Okay, but simple you have
and the
completed.
simple linear regression I have completed. Yes.
Okay, okay. And Miss Priyanshi, what about you?
I have half completed of the week 2.
Okay,
Just week 1 is fully completed.
okay, okay. Do you have, from whatever till whatever you've completed, do you have any specific doubts?
It
Yes,
was
ma'am,
fine to
about
go through
confidence
with the
interval.
assignment.
Just 1 second. Yes, Miss Priyanshi?
For week 1 assignment, it was okay. I didn't did my week 2 assignment. I just saw a few questions, but still I have to complete the videos, so
Okay,
not very well.
okay, okay. Yes. And Rose, what about you?
Can you explain confidence interval?
Confidence interval you've completed?
Ma'am, I have some doubts. Can you explain it again?
You have doubts?
Yes, ma'am.
Okay. Where exactly can you point me?
One second.
Hmm. Okay, today I will solve a few questions regarding confidence interval. Um,
Ma'am, is there any book sort of thing which we can go through for the revision type of, like, unlike going through all the videos, if we
hmm,
want to have a quick revision, then
okay.
what would you recommend for that?
There are multiple books, but I have to speak to the course instructor, and I'll talk to the professor and post the link to the books. Okay,
Okay,
there are
thank you, ma'am.
multiple books. Okay, one last question, Rose.
Ma'am, can you explain confidence interval again?
Yes, okay. So while I solve questions, I'll try to explain and what is going on, what's happening. So that you have problem in understanding or in um, the derivation.
Understanding.
Okay, okay, fine. Okay, so first I'll just start with uh, the recap of week 2. So far in week 1 we have learned that if we have, say, this is x and this is y, we have a few coordinates and we want to know the if there exists a linear relationship or not. So this one is my beta naught hat, the fitted curve, plus beta 1 hat plus x, where these are the estimates of the intercept and this is the slope. Right? Now, if we are to judge if this regression is significant or not, then what should we do? Do you think? Which of these parameters should you think we should test? So let's say this one is not significant, then irrespective of let's say this one is 0, I'm saying not significant, you consider this is 0 or very close to 0, then y naught equal to beta naught hat, we'll have something like this. So then what, then we could say that there exists no linear relationship between x and y, because whatever be the value of x, y is always this one, y is constant. So if we have to make this significant, we have to ensure that this slope parameter is not equal to 0. Then only the value of x will depend on the value of y will depend on, in some way depend on the value of x. It will be linearly related. So in order to assess if the regression is significant or not, what we do, we test the hypothesis, the original this beta 1 equal to 0. If this is not equal to 0, then we say it is significant. But if beta 1 equal to 0, then this is insignificant. Now this testing, as we have seen in the lectures, this testing can be done using an ANOVA approach, where this is the sum of squares due to regression, this one is sum of squares due to this is the sum of squares of residuals, here E means residuals, and these have been derived in the lecture notes, and this is the total sum of squares. This one has a df of n minus 1, and this one also has df 1, and this one is n minus 1 minus 1 n minus 2, and this MSR equal to SSR by df, that is 1, and MSE is SS residuals by n minus 2. Okay, so then the F statistic, it comes out as for the regression, it is MS regression by MS residuals, which follows F1 comma n minus 2 distribution under H naught. And if this value, this F naught value is greater than F1 n minus 2 alpha by 2, then we say that this regression is significant. Okay. Any doubts? Okay, so just look at this table, ANOVA table. So just a second. Now if we have to so we have gotten estimates of SS regression and SS residuals. So how can we assess the proportion of variance explained? Variance of y. Anyone? This is nothing but the R square, which is the sum of squares. Sorry?
It's a coefficient of determination.
Yes, exactly. Coefficient of determination, it determines the proportion of variance of y explained. So this one will be SS.
SS regression upon SS total.
By SS total. Okay. And Then we proceeded to interval estimation. So what happens in interval estimation? Let's suppose we have some unknown parameter, that is beta, some population parameter. Now we have to find a range in which beta lies, so that the probability of it lying between these two points is 1 minus alpha. So if my alpha, let's say it's 0.05, then this one is 0.95. So what essentially we are asking, we are looking out is what could be the range within which, if beta lies, the probability of beta lying within those boundaries is 95%. Broadly speaking, this is the idea. Okay, so when we had to find out points x1 and x2 based on our sample, so that the probability of beta lying between x1 and x2 is high. So the lower alpha is, the higher 1 minus alpha will be. So the standard one is 95%. So then we say x1, x2 is the 95% confidence interval for that parameter, say beta. Now this one was so far was simple linear regression. Then it was extended to a multivariate setup, where instead of one predictor we had multiple predictors. For example, let's say our y is price of any of house. So this one, it could depend on floor area, it could depend on the location, it could depend on amenities in that location, it could depend on the number of rooms or special rooms or washrooms, etc. So in a single univariate setup we had only one predictors, but in a multivariate setup we have more than one independent variables. And the model was written like y equal to x beta plus epsilon, and this one is a vector where each would represent the effect of this would represent the effect of x3. Beta naught would be the intercept. This would explain the effect of x1 on y. So these things were covered. And how did we do the estimation of coefficients? It was the same thing. Why we have, say, data on n individuals, or in this case n house prices. So this y then we can write as y1 price of the first house, price of the second house, price of the nth house. This one we can write as let us write it like this. 1 if everyone has to have an intercept. So the order of this matrix is n cross k, and this one is k cross 1. And along with these, we also have an error term. Okay. So in order to get the coefficients, let us denote this vector as epsilon vector. We had to reduce this one, which is essentially summation ei square. This one, let's say this is the vector of my residuals. So we had to find out the coefficients, these coefficient estimates, so that this quantity, which is nothing but the residual sum of squares, this is minimized. Fine. And what else did we obtained the estimates of beta hat. The formula I'll again revisit. And this, in this multivariate case, in single variant case, what we had, SST, the degrees of freedom were n minus 1. This was explained by 1, and this one was n minus 2. Similarly, in this case, its total, sorry, just a second. The total sum of squares, this df remains n minus 1, because you see yi minus y bar, this, there exists one constraint. For the residuals, since we have in here, we see k parameters 1, 2, 3, 0 to k minus 1, that is k. So the residual sum of squares would have n minus k degrees of freedom. Why? Because if you look at the how the estimates are derived, when you differentiate this one with respect to each of the k parameters, we would have k normal equations. So that is why k normal equations equal k constraints in choosing ei. That is why this residual df will be n minus k, and due to the additive property, this will be k minus 1. So all of these things were covered in this lecture of week 2. So now I'll start with a few problems related to these topics. So just read this one. We had to consider a model y equal to beta naught plus beta 1 x plus epsilon, where beta naught is known. So previously beta naught was also unknown. We had to estimate it from our data set. Now for this problem, it's given that beta naught is already known. Then how do we calculate the least square estimate of beta 1? So this is our model. This is already known. Now, what is the fundamental technique to find out least square estimates? Anyone?
The formula of beta naught is y bar minus beta 1 x bar. So from there we can find the...
No, just a second. That is this formula that you are talking about.
Partial derivatives.
Yes, this one will not be in this case because it is already known. This is not an unknown quantity that we have to estimate. It's already known. So for this regression, we just have to estimate this quantity beta 1, because this is given, this is known to us. So in that case, someone was telling partial derivatives. So how should I start?
In this, first we in respect of beta naught, and then in respect of beta 1.
Okay, but the first and foremost step is to get the residual sum of squares. This one we have to first obtain. This one will be summation of yi minus beta naught minus. So again I am saying, since this quantity is already known, it is given to us. This is not, let's say there you have some price, okay, the price of a house. You know that it will not be less than, let's say, 50,000. And then you are adding parameter. Something is given like this. So this baseline thing is already known to you. In that case, you just need to estimate beta 1 hat from the model. So because this is known, our yi predicted will be beta naught plus beta 1 hat x. Okay. So we'll write this residual sum of squares as yi minus beta naught minus beta 1 hat x square. Now in this case, the only unknown parameter is beta 1. So we will just differentiate with respect to beta 1. Then we would have 2 yi minus beta naught minus beta 1 hat xi. Sorry, I missed the i's. Into xi, which is equal to 0. So in this case, summation ei xi equal to 0. This will be my normal equation. So if I try to solve it, then what am I getting? Summation xi into yi minus beta naught minus beta 1 hat xi square. This one is equal to 0. So if we take beta 1 so this one we can write as summation xi yi minus beta naught equal to beta 1 hat summation xi square. Then beta 1 hat is written as summation xi yi minus beta naught by summation xi square. Is it clear?
Yes.
Okay. So now, we have the estimate of beta 1 hat as summation xi into yi minus beta naught by summation xi square. So the next question is, what is expectation of beta 1 hat? So here beta 1 hat from this problem we have estimated as just a second. summation xi into yi minus beta naught by summation xi square. Now expectation of beta 1 hat will be expectation of by summation of xi square. So this one we can take the expectation inside, so it will be summation. Now xi is not random, xi is a non-random part, only yi is random, so we'll keep xi outside, and this one, this expectation we can take within the bracket. This will be expectation of yi minus beta naught by summation xi square. Again, since beta naught is a constant whose value is known, we can write this as expectation of yi minus beta naught by summation xi square. So yi was beta naught plus beta 1 x plus epsilon I. So as for the assumptions, we had three assumptions. Remember, expectation of epsilon would be 0, variance of epsilon would be sigma square. So since this one is 0, expectation of yi in this case would be beta naught plus beta 1 xi. Fine. So putting this one here, this beta naught and beta naught cancels, then what do we have? We have summation xi into beta 1 xi by summation xi square. So if we take beta 1 outside, we have summation xi square by summation xi square. These two cancel each other and we have beta 1. So beta 1 hat that we have obtained is unbiased for beta 1. Is it okay? Any doubts? Sorry, I can't hear you. Please.
No, madam. Perfect.
Okay, fine. So, next thing is to find out the variance of beta 1 hat. So, to find that out, again I'll start by writing the estimate. So, this one came out as yi minus beta naught by summation of xi square. So variance of beta 1 hat will be then variance of this entire thing, summation xi yi minus beta naught by summation xi square. Now again here, since so variance directly we cannot add, so variance of x1 plus x2 is always variance of x1 plus variance of x2 plus 2 covariance of x1 and x2. Okay, so now note one thing. Okay, let me write it as y, it will be easier to understand. Okay, if we have two random variables, let's say y1 and y2, variance of y1 plus y2 would always be variance of y1 plus variance of y2 plus 2 covariance of y1 and y2. Now here note one thing, the yi's, these are random IID random samples, which means that yi and yj for all I not equal to j, they are independent, and since they are independent, their covariance is 0. So in that case, when y1 and y2 are independent, only in that case this summation boils down to individual sum. Okay, individual sum of variance. So applying this over here, since this one is, let's say, x1 y1 minus beta naught plus x2 y2 minus beta naught. So since y's are independent, we have, and also another thing is there, if variance of ay will be a square variance of y. So by that logic, since this is a constant term, this is not random, this is constant, so we would have 1 by summation xi square whole square summation of xi square variance of yi minus beta naught. For the timing I am writing this. Now variance of yi minus plus minus anything, it is always yi, because it depends only on the scale. So this one would be summation of xi square variance of yi. Now as we know, here again yi, the model was yi equal to beta naught plus beta 1 xi plus epsilon I. This was a constant non-random part, so variance of yi was also equal to variance of epsilon I equal to sigma square as per the assumption on epsilon I. So here again then we have sigma square, since this does not depend on I, we are taking it out of the summation xi square by summation xi square whole square. So one of these will cancel, we'll finally end up with summation xi square. Is it fine?
Yes, fine.
Okay. So the next thing is, in this model, what is the degree of freedom of sum of squares of residuals? So when we were deriving, how many normal equations we had?
It's only one.
It's only one. Yes.
Okay.
Yes, only one normal equation we had.
N minus 1 is the degree of freedom.
Yes, exactly. Because we have this normal equation which puts a constraint on ey. We can choose only n minus 1 ey's freely. The remaining ey would be chosen as per this constraint. So the degree of freedom would be n minus 1, not n minus 2. So if you observe, when this was unknown, we had two parameters. So this one degree of freedom was n minus the number of parameters we had to estimate. But here this one is already known and this one is unknown. So we have n-1 as degrees of freedom. So based on what is known and what is known, we have to carefully apply the degrees of freedom and get the MS residuals. Okay, we just can't memorize it like that. To think and answer.
Excuse me, ma'am.
Ha.
If we reverse the question, that is beta naught is unknown and beta 1 is known. So degree of freedom is the same, n-1.
Yes.
But its
But if beta 1
expectation or variance is different, or it's same as in previous question.
See, if beta 1 is already known
and beta naught is unknown,
would we really need to investigate? The motto here is to investigate the value of y from x. So if we already know what beta 1 is, then we know the relationship.
Okay, means there is no effect on
so we have established that there is an one effect.
Okay.
So in that case, if the estimating beta naught, we can definitely do that, but then what would we have? Let's see. You are saying that beta naught, beta 1 is available.
Yes.
So we would have beta naught hat minus beta 1 xi. This sum of squares we would minimize. So then this would be constant, this would be constant. Differentiating with respect to this one, what would we have? 2 summation y minus beta naught minus beta 1 xi equal to 0. So beta naught hat would be summation yi minus beta 1 beta I xi.
Summation ei equals to 0.
Summation ei equal to 0.
Okay, in that case also expectation of beta naught is also beta naught, unbiased.
If we put if beta naught is this one.
Okay, we will do, ma'am.
Okay, so the next thing is how, if from this problem we have to estimate get a 100 into 1 minus alpha % confidence interval for beta 1. So first let us write down what beta 1 hat is. Beta 1 hat, as we know, this was xi into yi minus beta naught by summation xi square. Previously we also got this one, that beta 1 hat is beta 1. This is an unbiased estimate for beta 1, and variance of beta 1 hat was sigma square by summation xi square. This one we got previously. Now carefully look at this quantity. So if we split it, we can write it as summation xi yi by summation xi square minus summation beta naught summation xi by summation xi square. Now this part is some constant c star. Because beta naught is known, we can, and these are not random, so we can consider this to be a non-random thing, and some constant, because this is some constant. So beta 1, then if we take this thing as summation di yi where di equal to some xi by summation xi square. Then beta 1 hat is a linear combination of the y's. Is this clear?
Yes, ma'am.
Okay. So since we know that yi follows a normal distribution, so a linear combination of yi will also follow a normal distribution. Then the distribution that beta 1 hat follows is normal beta 1 and the variance is sigma square by
square upon summation
xi square. Now, so we can write this thing that beta 1 hat follows beta 1 sigma square by summation xi square. So then beta 1 hat minus beta 1 by root over sigma square by summation xi square, this would follow a normal 0 1. And previously we had seen that SS residuals by the sigma square, it was following chi square with the degrees of freedom of this SS residuals, whatever it was there. So in this case our DF is n minus 1 and these two are independent. So we know that a normal by root over mean chi square, it follows a t distribution. This one we know. So combining these two, if we write something like this, beta 1 hat minus beta 1 by root over sigma square by summation xi square divided by this one SS residual by sigma square mean divided by this one by n minus 1. This would follow a t n minus 1 distribution. Now this part SS residual by n minus 1 is nothing but ms residuals, and this sigma square will cancel with this sigma square and we will be left with beta 1 hat minus beta 1 by root over ms residuals by summation xi square. This would follow a t n minus 1 distribution. Is it clear so far?
Yes.
Okay. So
Yes,
so once we have obtained this thing, I'll just write it down again. Beta 1 hat minus beta 1 by root over ms residuals by summation xi square. This one follows a t n minus 1 distribution. Now let this be the PDF of a t distribution. Okay, it's a symmetric curve, and let this one be the upper alpha by 2 point and this one is the lower alpha by 2 point. So we have to find so this one we know that this area is 1 minus alpha because the total is 1. This area is 1 minus alpha. So if we write something like this, that probability minus alpha by 2 less than this one, since this follows a this is following t distribution, we can write this entire thing here, minus beta 1 by root over ms residuals by summation of xi square less than alpha by 2. This area is equal to 1 minus alpha. Okay, so if we rearrange, then can we write this minus alpha by 2 ms residuals by sum of xi square less than beta 1 hat minus beta 1 less than root over ms residuals by summation xi square alpha by 2. This one equal to 1 minus alpha. So from this one we have probability minus alpha by 2 root over ms residuals by summation xi square less than beta 1 hat minus beta 1 less than alpha by 2 ms residuals by summation of xi square equal to 1 minus alpha. So now we want a range for the unknown one, that is beta 1. This one we have already estimated. So we want a confidence interval for, always remember, the unknown parameter. So if we rearrange and write beta 1 in the center, then this is less than, if we take it this side, then beta 1 hat minus alpha by 2 root over ms residual by summation of xi square. Just considering this part, we can write this, can we write this taking this to the left and this one to right, that beta 1 is less than beta 1 hat plus alpha by 2 root over this thing. Similarly, when we are considering these two, beta 1 is greater than this one. If we take to the left, then what do we have? Beta 1 hat minus alpha by 2 root over ms residuals by summation of xi square. So this probability is 1 minus alpha. So this is what we wanted. We wanted some values within which if beta, the probability of beta lying is equal to 1 minus alpha. So these will be my confidence interval. Therefore 100 into 1 minus alpha percent Ci for beta 1 is this thing, beta 1 hat minus alpha by 2 root over ms residuals by summation of xi square and beta 1 hat plus alpha by 2 this thing ms residuals by summation xi square within third brackets. Is it clear?
Yes.
Okay.
Yes, ma'am.
Rose, is it clear to you?
Yes, ma'am. Yes, ma'am. Clear.
Okay. This is how you find out a confidence interval. So now if instead of beta we have to find 100 into 1 minus alpha confidence interval for mean response at the value of x equal to x naught. So first of all, what do we mean by this thing? Anybody? so far this is, let's say, this one was my model. So far I was finding out a confidence interval for this one. When it is said that we want the mean response at a certain value, we mean that we want the confidence interval of this thing, x equal to x on. This means expectation of y at x equal to x naught, a confidence interval for this quantity. Okay, so from here you see expectation of expectation of y will be what? Beta naught plus beta 1 x. Since epsilons are 0, we have already considered. So expectation of y at x equal to x naught will be, we just substitute the value of x naught here. It is beta naught plus beta 1 x naught. So this one is my known quantity, this is not known. As a result, this one is also not known. So if we have to estimate, then we have to estimate this one. Then this becomes my estimator. Now I am to check that if this is an unbiased, is it unbiased? How will I check that? Expectation of the entire thing equal to expectation of beta naught plus beta 1 x naught equal to this hat we are taking expectation of. This is beta naught plus expectation of beta 1 hat into x naught. Since this is unbiased for this problem, it will be beta naught plus beta 1 x naught, which is equal to expectation of y given x equal to x naught. So it's unbiased. Now we are to find the variance. From here we'll find the variance of this quantity. 1 second, I'll just draw it properly. This one would be entire thing. So we have here expectation of y at x equal to x naught. This one is beta naught plus beta 1 hat x naught. So variance of this one would be, since the only quantity here is the random quantity is beta 1, which is a linear combination of the y's, we would only have x naught square variance of beta 1 hat. And what was this? X naught square variance of beta 1 hat was sigma square by summation of xi square. This one we have derived earlier. So now, following the same logic, we can write that x equal to x naught, since it depends on beta 1 hat, which in turn depends on y. This is a linear combination of the y's. If that follows normal, this will also follow normal. So this would follow then beta naught plus beta 1 x naught and sigma square x naught square by summation xi square. So following the same logic, we can write expectation of y this thing minus beta naught minus beta 1 x naught just a second, this will be beta naught hat. Sorry, so this one by root over ms residuals by x naught square by summation xi square. This would also then follow a t n minus 1 distribution. And similarly we would construct my pen is not working, I'm sorry. Okay, so you understood, no? So from here only, similarly like we constructed here these limits as we constructed using 1 minus alpha, similarly we would construct a confidence interval from this line, from this portion itself. We'll just keep this in the center and then take alpha by 2 in each side, and then we would find out, we'll keep this thing in the middle, and then we would find out the rest of the things. I hope this is clear to you. So in the next doubt clearing session I will be doing another of these problems on the prediction interval and how we can solve that, and we'll move on to multivariate linear regression. So if you have any questions, please ask. Any questions?
Yeah.
Okay, so okay then, thank you so much for joining. If you do have questions, then post it in the discussion forum and I'll try to see and get I'll try to get books and share the links with everyone.
Okay. Thank you.
Okay, thank you so much.